Welcome to chapter 4, which is about thread. So today we're going to talk about the basic components of a thread, what threads means, and how do we compare them to processes. Then we'll describe the benefits and the challenges of designing multi-threaded applications. Then we will illustrate the different approaches to implicit threading, including thread pools and fork join. So a thread is a basic unit of CPU utilization. It has a thread ID, a program counter, a register set, and a stack. It shares with other threads that belong to the same process the code section and the data section, as well as other operating system resources such as the open files and the signals. So a traditional process typically has a single thread of control, but if a process has multiple threads of control, it can perform more than one task at a time. Now, most software applications that run on modern computers and also mobile devices are currently multi-threaded. So an application typically is implemented as a separate process with several threads. An example of multi-threaded applications, for instance, a word processor that may have one thread for displaying graphics, another thread for responding to I/O operations in the keyboard from the user, another thread for performing spelling and grammar check in the background, and so on. So this figure illustrates the difference between a traditional single-threaded process versus a multi-threaded process. You can see that inside one process we can have multiple threads, each have its own program counter, stack, registers, files, and so on. So let's take a look at this scenario where a server runs a single process that accepts requests from clients. Remember, we talked about this in the client-server architecture, right? So when the server receives a request, it creates a separate process to service that request, okay? So this process creation method was very common before threads were invented or became popular. Now, process creation, keep in mind that it's very time consuming and resource intensive. Whereas if the new process will perform the same task as the existing process, so why the overhead? Why create a new one? So it's generally more efficient to use just one process, but one that has multiple threads, right? So if the web server process is multi-threaded now, the server will create a separate thread that listens for client requests. When a request is made, rather than creating another process, the server creates a new thread of the same process to service the request and then continues listening for additional requests. So most operating system kernels are also typically multi-threaded. As an example, during system boot time on Linux systems, several kernel threads are created. Each thread will perform a specific task, for instance, managing devices, memory management, interrupt handling, and so on. So for the programmers or developers that they want to develop some very CPU-bound problems or applications, like for instance in AI or data mining, they can leverage the power of the modern multi-core systems by designing solutions that are multi-threaded and that can run in parallel. So the benefits of multi-threaded programming can be divided into four major types or four major categories. The first is the responsiveness. So, for instance, consider what happens when a user clicks a button and that results in the performance of a very time-consuming operation. In a single-threaded application, it would be unresponsive to the user, right, until the operation has finished. Whereas if the that time-consuming operation was performed in separate asynchronous thread, in an asynchronous thread, right, the application can remain responsive to the user. Also, the other benefit is resource sharing. So processes can share resources only through techniques such as shared memory and message passing that we're going to talk about later in this lecture. However, threads do share the memory and the resources of the parent process to which they belong. So economy, of course, the threads are cheaper than thread creation is cheaper than process creation, and it's faster to context switch between threads than to switch between processes. So the benefits of multi-threading can be even greater in multiprocessor architecture, where threads may be running in parallel concurrently on different cores, right? Remember we talked about multi-core processors. So here we can leverage that when we create multi-threads that they can run simultaneously. So with single-threaded process, it can run on only one processor, so regardless how many are available. So that's a waste of resources if we had only single-threaded processes. So this is a good figure to describe the relationship between threads and processes. So what we're looking here is a single-threaded process that has a single program counter, right? The traditional scenario that we talked about in chapter 3. Now the program counter keeps moving through the program as the execution continues. Now a process with multi-threads can have a separate program counter for each one of his threads. And the multiple program counters, they can carry on and advance through the code independently from one another, and each thread can execute a different sequence of instructions within the same code. Now, when multiple CPUs are available, the threads can even proceed in parallel simultaneously. So this figure looks at multi-threaded processes from the PCB point of view, right? So in a single-threaded process, it only has one program counter and one stack pointer, and the process state in the PCB may be, as we talked about, can be running, ready, blocked, right? Now the CPU state is replicated in each thread TCB, giving each one of them a private program counter and stack pointer. Now the process state is replicated as a thread state in each one of the TCBs. Then each thread can be in any state independently, right? So one can be running, the other can be blocked, the other thread can be ready, and so on. Now the other fields, like the memory, for instance, remains in the process PCB. So each thread can access the shared code using their own private program counter, and they can advance executing their own section in the code independently. Each thread can also have a private stack of its own, and it can access it using its own stack pointer.